Hey everybody, my name is Calvin and welcome back to my channel. In this video, we're going to be walking through the Bellman-Ford shortest path algorithm. If you watch my Dijkstra video, you'll already know the basic idea of shortest paths in a weighted graph. If you haven't, it's linked right there in the top right. Dijkstra works great when all edge weights are non-negative. Bellman-Ford solves the same problem, but with one big advantage, in that it can handle negative edge weights and it can detect negative cycles. The trade-off is that Bellman-Ford is slower than Dijkstra, but it is more flexible. So anytime you see negative weights or you need to check whether a negative cycle exists, Bellman-Ford is the tool you want. In this video, I'll explain Bellman-Ford at a high level, we'll implement it in Python, and we'll walk through a couple examples. As always, the GitHub repository will be linked in the description, so if you'd like to follow along, the code is right there. Let's start with what the algorithm is doing conceptually. Bellman-Ford solved the single source shortest path problem. First, you have a directed weighted graph, and each edge has a weight that can be either positive or negative. You pick an arbitrary starting node, and the goal here is to find the minimum cost to reach every other node from that specific start node. Just like Dijkstra, Bellman-Ford keeps a distance table. For each node, what is the best distance we have found so far from the start node? At a high level, the algorithm is like this. First, we set the distance to the start node to 0, and then we set every other distance to infinity. We want to repeat the following step v 1 times, where v is the number of nodes. We look at every edge u to v with a weight of w. If going from the start to u, and then along this edge to v, gives a shorter path than what we have recorded for v, then we update the distance to v. This is called relaxing the edge. After those v1 passes, we have the best distances as long as there exists no negative cycle. Then we do one more pass over all edges to check whether any distance can still be improved. If yes, that means there is a negative cycle reachable from the start node. In that case, there is no meaningful shortest path because you can loop and make the cost smaller forever. So you can kind of look at Bellman-Ford in two phases. A repeated relaxation phase to spread distance updates across the graph, and then a final check to detect negative cycles. For our algorithm, we'll be using a very simple graph representation in Python. The same style as the Dijkstra video from before. I'll represent the graph as a dictionary that maps each node to a list of neighbor and weight pairs. For example, from node A, we can reach B in 4 steps, and then C in 2 steps, B to C in -1 steps, and B to D in 2 steps. This is a negative weight, and this is just a positive weight. C to D to 3 steps, D to E 2 steps, and E is the end node. That's the structure that the plain Bellman-Ford implementation will use. Now, let's write the Bellman-Ford function. It'll take this dictionary-based graph and a start node that we pass in, and it returns a distances dictionary, mapping each node to its shortest distance from the start, and then a predecessor dictionary that tells us which node we came from on the best path. Let me walk through what this function is doing. First, we import math so we can use math.infinity. For every node in the graph, we set its distance to infinity, except for the start node, which we set to 0 because from our start node to the start node is trivially 0. This matches the idea that we know the distance from the start to itself, and we know nothing about the others yet. We also create a predecessor dictionary and then initialize everything to none. We count how many nodes are in the graph and store that in num nodes. Then comes the main loop. We run the relaxation phase num nodes -1 times, and inside that loop, we set a flag called updated to false. Then we iterate over every node u and every outgoing edge u to v with a weighted w. For each edge, we check whether we can improve the distance to v by going through u. In code, we have this check. This part compares the old distance to v with the candidate distance that goes through u. If the candidate is better, we update distance v and record that the best way to reach v is now from u, by setting predecessor v is equal to u. We also set updated to true to remember that something changed in this pass. At the end of the pass, if updated is still false, that means we went through all edges and did not improve any distance. In that case, we are already done and we can break early. That's a nice optimization for graphs where distances can converge quickly. After the relaxation loop, we do one more pass through all edges to detect negative cycles. If we can still improve a distance at this point, it means that there exists a negative cycle reachable from the start node. In that situation, the algorithm cannot produce a meaningful final table of shortest distances, so we have it set up to throw a value error. If the last pass does not find any improvements, then our distances are final. We return the distances and predecessor dictionaries. In addition to this plain function, I also have a second helper called Bellman-Ford with GIF. It uses NetworkX and Matplotlib to draw the graph and capture each relaxation step as a frame, then stitches those frames into a GIF. Our helper function here uses the same logic as the plain Bellman-Ford algorithm we just wrote. It just visualizes the process, so we'll just ignore that. Let's start with a small example to make this concrete. First, we build a graph with nodes A through E. There is one negative edge weight, but there exists no negative cycle. This is the same structure as before, but just using a NetworkX graph that we can pass into the GIF generating helper. Conceptually, this graph looks like this. From A, you can go to B with a cost of 4, and C with a cost of 2. You can go to B to C with a cost of -1, and to D with a cost of 2. C to D, cost of 3, D to E, cost of 2. So when we run our function, the algorithm will do the following. Initially, we set distances at A to 0, and then everything else is infinity. In the first pass, it relaxes edges and discovers A to B costs 4, so distances B becomes 4. A to C costs 2, so distances C becomes 2. Using B to reach C costs 4 plus -1 equals 3, which is no better than 2, so the shortest distance stays at 2. From B to D costs 4 plus 2 equals 6, so distances D becomes 6. From C to D costs 2 plus 3 equals 5, which is better than 6, so D improves to 5. From D to E costs 5 plus 2 equals 7, so distances E becomes 7. In later passes, the algorithm keeps checking all edges, but it doesn't find any further improvements. So finally, the distances will stabilize at A to 0, B 4, C 2, D 5, and E 7. The predecessor dictionary tells us the best parent for each node, so you can reconstruct the actual paths. For example, A to C, to D, to E for the path to E. Feel free to slow down the video to visualize the algorithm right here. Now, let's look at a slightly larger example where the nodes are numbered instead of labeled with letters. This graph has several negative edges, but still no negative cycles, so Bellman-Ford will converge to a well-defined answers. Here, we have our NetworkX directed graph, which I will pass into my Bellman-Ford with GIF helper to generate the animation. Let's walk through what's going on in this graph. From node 1, you can go to 2, 3, or 4 with different costs. From 2, you can go to 5 with negative weight of -1, 3 to 2 with a weight -2, and 5 with weight of 1, and so on. There are negative edges, but notice that there is no way to loop around and come back to the same node with a lower and lower cost, so there exists no negative cycle. When we run our Bellman-Ford algorithm, the algorithm starts with distance 0 at node 1 and infinity everywhere else. As it relaxes all edges over multiple passes, it gradually discovers cheaper and cheaper paths. It finds that going from 1 to 4 to 3 to 2 is cheaper than directly going 1 to 2. It uses the negative edges from 3 to 2 and from 4 to 3 to drive the cost to node 2 down to 1. From there, it reaches node 5 very cheaply, and then 7, it also discovers a path to node 6 through node 4. Feel free to slow down the animation to follow along with what the algorithm is doing. After the relaxation finishes, the final shortest distances from node 1 are distance to 1 is 0, distance to 2 is 1, distance to 3 is 3, distance to 4 is 5, distance to 5 is 0, distance to 6 is 4, and then distance to 7 is 3. We can see that this is cooperated in our GIF and our output. The predecessors dictionary right here shows which node each of these came from, so you can reconstruct full paths like 1 to 4 to 3 to 2 to 5 to 7 for the best route to node 7. And that's that. What makes Bellman-Ford so interesting is how methodical it feels compared to other algorithms. You can almost watch the information ripple through the graph, each pass updating one more layer of nodes until everything stabilizes. When you include negative weights, that propagation becomes even more powerful because the algorithm can uncover cheaper paths that other algorithms would miss. This also explains why it runs slower than Dijkstra. Bellman-Ford doesn't rely on a greedy step. It systematically checks every edge, making sure nothing is left out. That patience is what allows it to handle more complex graphs safely. When you watch the GIFs, you can actually see this story unfold. The distances don't jump to their final values all at once, and they spread step by step as each edge gets relaxed. It's a great reminder that some algorithms aren't just about getting the answer quickly, and they're about guaranteeing that you find the right one. If you found this walkthrough helpful, please don't forget to like and subscribe, and I'll see you guys in the next video. Thanks for watching.